Okay, so we are back again. Whatever we finished in your previous lecture, so we are starting only from that point, right? So earlier we have seen that inductance is directly proportional to the permeance, which as indicated earlier has a second harmonic variation, right? The inductance LAA, right? Actually LAA, LBB, LCC, you will see there, these are the your self inductance, right, of A means phase A, B means phase B, and C means phase C, right, will be a maximum at theta is equal to 0 degree and a minimum of theta is equal to 90 degree, right, and again a maximum at theta is equal to 180 degree and so on, right. So that means, just hold on. So if we neglect the space harmonics, right, if we neglect the space harmonics, right, the MMF of phase A has a sinusoidal distribution in space with its peak centered on the phase A axis, right. The peak amplitude of the MMF wave is equal to the NAIA, that was, I mean, it is your number of your ampere turns, right, NAIA, where NA is the effective turns per phase, right. So as shown in figure 13, I will show you that in the previous lecture also we have seen that this can be resolved into two other sinusoidally distributed MMF, right. So if we come to this, right, so and centered on the D axis and the other on the Q axis. So this is the diagram we have seen earlier. So this is your MMF A and this is your MMF AD, right, D axis one, and this is another one, that MMF AQ, this is MMF AQ, right, and from this point, that phase A axis point, theta is measured. So this is theta, and angle between Q axis and D axis is 90 degree. So from here if you measure, it will be theta plus 90 degree, right. Now if you resolve this one in a Q axis and D axis component, so this side on D axis it will be NAIA cos theta, and on D axis will be minus NAIA sin theta, because it will be NAIA cos 90 degree plus theta, right. So that will become minus NAIA sin theta. So D is D axis and this is Q axis, and this is the resultant one, MMF A, right. So this is actually figure 13, phase A MMF wave and its component. Now the peak values of the two component waves, now here it is given that MMF AD will be NAIA cos theta, right, and MMF AQ will be NAIA cos 90 degree plus theta. I told you that will be minus NAIA sin theta. This is equation 31. Now next is the reason for resolving the MMF into the D axis and Q axis component is that each acts on specific air gap geometry of defined configuration, right. So air gap fluxes per pole along the two axes are, right. So it is actually synchronous machine. When we will go through that, we will see that every time that this little bit your what you call I mean some based on certain assumption we will make, and another thing is that we will try to see that as simple as possible to represent this kind of thing. Therefore air gap fluxes per pole along the your two axes are given. So air gap flux phi g AD as in D axis, it will be NAIA cos theta into PD, right. So that we will see that PD and PQ are the permeance coefficient of the D axis and Q axis respectively, and this is NAIA cos theta into PD, because we know that in general flux is equal to ampere turns into permeance. This we have seen when we are brushing up our memories for your coupled circuit, right. Similarly for phi g AQ, this we have seen the component minus NAIA sin theta into PQ, right. So this is equation 32 and this is equation 33. Now in the above, PD and PQ are the permeance coefficient of the D and Q axis respectively. Now in addition to the actual permeance, they actually include factors required to relate flux per pole with peak value of the MMF wave, right. Therefore the total air gap flux linking phase A is actually it will be phi g A, this is that your this is your that total air gap flux linking per phase will be, that is phi g A, right, is equal to phi g A d cos theta and minus phi g A q sin theta. Now from previous expression you substitute here that your phi g A d is equal to N A I A P d cos theta from the previous equation, that is your 32 and 33, and similarly phi g A q you put it as minus N A I A, that from previous expression sin theta into P d. These two if you substitute, that means from previous expression that phi g A d is equal to N A I A cos theta, right, that you substitute here, then it and your into your what you call into your P d, right. So if you substitute here, it will be N A I A P d then cos square theta, because cos theta into this cos theta, cos square theta. Similarly for phi g A q from the equation your 33, right, phi g A q is equal to minus N A I A your sin theta into your P q. So you substitute here this expression, you substitute here, so it will be plus, then your N A I A will be common because this is in bracket, N A I A is common, basically it will become N A I A P q sin square theta, right. So now let me clear this. Now after that you simplify this one, because we know that your cos 2 theta is equal to 2 cos square theta minus 1, that means your cos square theta is equal to 1 plus cos 2 theta divided by 2. So cos square theta you substitute here 1 plus cos 2 theta by 2. Similarly for sin square theta, again, that cos 2 theta is equal to 1 minus 2 sin square theta, that means sin square theta is equal to 1 minus cos 2 theta by 2, right. Here also you substitute and then simplify. If you do so, you will get N A I A, then P d plus P q by 2 plus P d minus P q by 2 into cos 2 theta. So this is equation 34, right. I hope this part is understandable. Now once you have done, right, just hold on, we will go to the your next one, right. So now therefore we know this, the self inductance LGAA of phase A due to the air gap flux is, it will be n, general formula is n phi upon I, right. Therefore your this LGAA, right, the self inductance LGAA of phase A due to air gap flux will be Na phi GA upon Ia, right. So that phi GA expression we have seen, you substitute here. In that case what will happen, Ia will be cancelled and Na will be multiplied, so it will be Na square sorry, plus Pd plus into Pd plus Pq upon 2 plus Pd minus Pq upon 2 into cos 2 theta, right. So this equation, this one is equal to, we can write Lg0 plus Laa2 cos 2 theta. That means one thing is that Lgaa is not a constant, it is function of theta, right. So where Lg0 is equal to your Na square into Pd plus Pq upon 2. So it is given Na square into Pd plus Pq by 2 and Laa2 will be Pd minus Pq by 2. So this is into Na square, right. So the total self inductance Laa is given by adding to the above the leakage inductance Lal. I mean we are considering, say, some leakage inductance is also there, right. Just your some leakage inductance Lal is there, capital A suffix is small al there, which represent the leakage flux not crossing the air gap. So very small amount, but I mean we are adding to this. If we do so, then it will be Laa will be L capital Lal plus Lgaa, right, which is actually, now this Lg0 Lal is there, then LGAA is equal to LG0 plus LAA2 cos 2 theta, right, and this can be written as LAA0 plus LAA2 cos 2 theta. Actually this little bit of leakage flux will be there, which is not crossing the air gap. So along with it you have to add this, right. So if it is so, and LGA is equal to LG0 plus LAA2 cos 2 theta, all LG0 and LAA2 we have defined just in the previous page, right. So this can be totally, it can be written as your LAA0. So LAA0 is your this term LAL plus LG0, and this is LAA2 cos theta. This is equation 36, right. So therefore LAA0 is equal to LAL plus A0. Since the windings of phase B and C are identical, right, because it is a symmetrical winding and 120 degree apart, right. So that the phase A and are displaced from it by 120 degree and 240 degree respectively, right. So similarly, therefore LBB and LCC will get, because we write LA0, we will not write LBB0 or LCC0 because they all are same from the symmetry, right. So LBB is equal to, instead of writing LBB0, LCC is equal to LCC0, because all are same, LA0 is equal to LBB0 is equal to LCC0. So we are representing only this term LA0 again and again, right. Similarly, this term also from symmetry we will not write BB2 or CC2, will same thing, because only 120 degree apart, but this magnitude will remain same, right. Therefore LA0 will be LA2 cos 2 into theta minus 2 pi by 3, right, because 120 degree apart. And second one LCC will be LA0 plus LA2 cos 2 into theta plus 2 pi by 3. This is equation 37 and this is equation 38. So only we are finding out that LA. After that, from the symmetry we are just replacing the theta by theta minus 2 by 3 for phase B, and for phase C, that is it is theta, your what you call replacing theta by theta plus 2 pi by 3, right. So the variation of LA with theta is shown in figure 14. So this is the variation of LA. So if you come to this, that your expression for your LA, right. So your this is your what you call, this is your LA. So when theta is equal to 0, therefore your maximum value will be LA0 plus LA2, right. And when theta will be is equal to pi by 2, right, that means theta pi by 2 means 2 theta is equal to pi. So it will be LA0 minus LA2. So maximum plus and minimum minus. So if you plot this, the plotting will be like this, right. When theta is equal to 0, it is this is the your what you call that maximum, that positive value. When it is theta your pi by 2 90 degree, it is the minimum one, right. And this is your, this part is LA2, and this LA0 is constant, because LA0 plus LA2 cos 2 theta. So this is your LA0 line. I mean this is your LA0, right, because this part is LA0, and this part your what you call, from this part is LA0 plus LA2, and this part is LA0 minus LA2, right. So this is your plot of LA versus theta, variation of self inductance. So it is not a constant, it is varying with theta, right. Now in equation 36 and 37 and 38, the stator self inductances have a fixed plus second harmonic terms, right. That is, fixed term is LA0 plus you have some term LA2 into cos 2 theta, right. Higher order harmonics terms have been neglected for this study, otherwise things will become complicated. So in a well designed machine in which the stator and rotor windings produce nearly sinusoidally distributed MMF and flux waves, these higher order harmonics terms are negligible, very small, that is why it is neglected. Now stator mutual inductances. The mutual inductance between any two stator windings also exhibits a second harmonic variation. because of the rotor shape, right. It is always negative and has the greatest absolute value when the north and south poles are equidistant from the centers of the two windings concerned, right. So, the mutual inductance between any two, so your what you call stator windings, that is in between phase A or B, B or C or C or A, right, exhibits second harmonic variation because of the rotor shape, right. It is always negative and has the greatest value when the north and south poles are equidistant from the centers of the two windings concerned, right. For example, suppose LAB has a, it is between your phase A and B of stator winding, right, has maximum absolute value when theta is equal to minus 30 say or theta is equal to 150 degree. The mutual inductance LAB can be found by evaluating the air gap flux phi GBA linking phase A when only phase A is excited. The way when we are revising that your coupled circuit, right. So, same philosophy. So, the mutual inductance LAB can be found by evaluating the air gap flux phi GBA linking phase B when only phase A is excited, right. So, now as we wish to find the flux linking phase B due to MMF of phase A, right. So, theta is replaced by theta minus 2 by 3 in equation. This is very important. You need not derive many things. Look, as we wish to find the flux linking phase B due to MMF of phase A, so then theta is replaced by theta minus 2 by 3 in equation 34, right. So, from our intuition we can make this one. So, that means that phi G B A, right, is equal to phi G A D, just same thing we are writing, replacing theta by theta minus 2 pi by 3 cos theta minus 2 pi by 3 minus phi G A Q sin theta minus 2 pi by 3, right. Now, if we substitute the expression of phi G A D, that was NA IA P D cos theta, and here also phi G Q, if we substitute minus NA IA your what you call sin theta into PQ, if you substitute, then it NA IA you will take common, then it will be PD cos theta into cos theta minus 2 pi by 3 plus PQ sin theta into sin theta minus 2 pi by 3. Only same expression earlier whatever we did phi G A A, right, just we are replacing theta by theta minus 2 pi by 3, that was in equation 34, right. So, if you simplify this one, this is a small exercise for you, because if I try to do all these things here, then it will consume more time, right. So, if you just simplify this one, then it will become your what you call minus PD plus PQ upon 4 plus PD minus PQ upon 2 cos 2 theta minus 2 pi by 3, right. So, this way your what you call this has been simplified. So, this is actually cos A cos B and this is your sin A sin B, and just from that just giving you some hint. So, try to derive this one, right. So, if you make it, it will be coming like this. So, this is equation 39 after simplification. Now, the mutual inductance between phases A and B due to the air gap flux is, now we have to find out the mutual inductance between phases A and B due to the air gap flux, that means LGBA, right. This is the mutual inductance between your what you call phases B and A, it will be NA into this your phi GBA divided by the current, because phase A is excited. So, divided the current in phase A. So, it will be NA phi GBA upon IA. Now, if you substitute the expression from here, phi G, this is your phi GBA, this is your phi GBA, right. You substitute, your IA will be cancelled, and it will finally, after simplification we can write that LGBA will be minus half LG0, capital LG0 plus capital L AB2 cos 2 theta minus 2 pi by 3. This is equation 40, where L AB2 will be NA square into PD minus PQ upon 2. You substitute and simplify, right. Then you put in this form, and LG0, right, and where LG0 has the same meaning as in the expression for self inductance LGA given by equation 35. So whatever Lg0 is there in equation 35, same meaning. So just you put it and simplify and get in this form, right. So it will be LAB2 will be n square into PD minus PQ by 2. So there is a very small amount of mutual flux around the ends of windings which does not cross the air gap, that we discussed earlier also. With this flux included, the mutual inductance between phases A and B can be written as, we can write LAB is equal to LBA from the symmetry, right, is equal to minus say LAB0 plus LAB2 cos 2 theta minus 2 pi by 3, or we can write this is minus LAB0 minus LAB2. This expression after simplification can be written as cos 2 theta plus pi by 3. This is equation 41, right. This little bit you do from your side, right, directly I am writing. So this equation can be written like this, but here it is plus, now it is minus, and it is 2 theta plus pi by 3, right. Similarly, this is LAB is equal to LBA. Similarly, because from your what you call that windings are 120 degree apart, similarly LBC is equal to LCB will be, it will remain as it is minus LAB0, it will remain as it is minus LAB2, because their magnitude for all these things are same. So, we are not making it, your BC means not making it BC0 or BC2, right, just because magnitude remains same, this way, I mean LAB2 is equal to LBC2 is equal to LCA2 like this. So, all are same, only thing is that their things are 120 degree apart. So, this one will be cos 2 theta minus pi, this is pi by 3, it will be cos 2 theta minus pi, and similarly LCA will be LAC will be minus LAB0, then minus LAB2 cos 2 theta minus pi by 3, because 120 degree plus 240 degree it is apart. So, this is your, this way you can write. If you just try to see this one, then you will see the difference will be 180 degree, 120 degree, right. So, this is equation 41, this is 42, and this is your 43. Now, from the above equations, it can be readily seen that LAB2 will be is equal to your LAA2, right. So, all this expression, if you see that whatever has been done, whatever has been simplified, right, that LAB2 is equal to LAA2, because earlier we have seen, no, LAA2 is equal to n square PD minus PQ by 2, and this is nothing but also is equal to LAB2, right. So that is why it is written LAB2 is equal to LAA2, right. Now, this is to be expected since the same variation in permeance produces the second harmonic terms in self and mutual inductances. It can also be seen that LAB0 is nearly equal to half of LAA0, right, if you neglect that your leakage one. So, this is your what you call, that is your mutual inductance between the these are all these expressions, this is your mutual inductances between the two phases of stator winding, right. Next is the mutual inductance between stator and rotor windings. Now, with the variation in air gap due to stator slots neglected, the rotor circuits see a constant permeance, because we have to make some assumption to simplify our analysis, right. So, this is now for rotor windings we have to obtain. So, with the variation in air gap due to stator slot neglected, the rotor circuits see a constant permeance, right. Instead, the variation in the mutual inductance is due to the relative motion between the windings themselves, right. So, that means when a stator winding is lined up with a rotor windings, when a stator winding is lined up with a rotor winding, the flux linking the two windings is maximum and the mutual inductance is also maximum, right. I mean, when a stator winding is lined up with a rotor winding, the flux linking the two windings what you call is maximum and the mutual inductance is also maximum, right. And when the two windings are displaced by 90 degree, right, no flux links the two circuits and the mutual inductance is 0, right. So, therefore, with a sinusoidal distribution of MMF and flux waves, we can write this is your what you call, we are this is FD means field circuit, and this side your it is basically it is your what you call, this is mutual inductance between stator and rotor windings, right. So, therefore, it is between your field is on the rotor, and this is LAFD. So, we can write that LAFD is equal to capital LAFD, this is a peak value, say cos theta, right. And on the direct axis, apart from this field winding, you have the armature winding, right. Therefore, small LAKD is equal to capital LAKD cos theta. This is equation 45, right. Similarly, on the quadrature axis, right, you have only that armature winding. So, it will be small AKQ will be capital L AKQ cos theta plus pi by 2, because direct axis and quadrature axis, the angle between these two axes is 90 degree. That is why it is cos theta plus pi by 2, that is actually is equal to minus capital L AKQ sin theta. This is equation 46, right. So, this is actually between stator and rotor, that your mutual inductance, this expression. Now, for considering the mutual inductance between phase B winding and the rotor circuit, theta is replaced by theta minus 2 pi by 3, and for phase C winding, theta is replaced by theta plus 2 pi by 3, because same philosophy from the symmetry, it is same philosophy. Therefore, we now have the expressions for all the inductances that appear in the stator voltage equation, right. On substituting the expression for this in equation 29, we are not going back to equation 29, but just whatever flux linkage equation written for phase A, what you do, you substitute all, then you will get psi A will be minus IA into LAA0 plus LAA2 cos 2 theta plus IB into LAB0 plus AA2 cos 2 theta plus pi by 3 plus IC into LAB0 plus LA2 cos 2 theta minus pi by 3, right, plus you will see IFD LAFD capital LAFD cos theta plus IKD capital LAKD cos theta, then this one minus your IKQ L capital LAQ sin theta, this will be equation 47, right. So, whenever you that all the flux linkages, I am not going to just hold on, if your equation 29, right, I have to find out which page it is. So, equation 29 probably here, right. So, this is your, just hold on, just hold on, equation 29, I will see where it has gone, just hold on. Not this one. So, here only. So, just have a look that equation, this is equation 29, right, and here we actually this minus LAIA minus LABIB minus LACIC plus all these things, right. So, just you have to substitute LA expression of LAA, LAB, LAC, and here also you have to substitute your LAFD, LAKD and you substitute, right, and then only you will get this your what you call this expression psi A, right, it will be minus IA whatever it is. So, this is equation actually 47. Thank you very much, we will be back again.